Your city's cooling strategy might be failing you right now. Scientists are uncovering why planting trees and painting roads can actually make heat waves worse. Everyone knows that as global temperatures rise, our concrete jungles are turning into unlivable ovens. And you have probably heard the standard, universally accepted solution that urban planners have been pushing for the last 2 decades. To save our cities, we are told we must increase the albedo effect by painting impervious surfaces white, and we must plant millions of trees to create a natural cooling canopy. When you look at the basic physics, this strategy makes complete and total sense to anyone who has ever worn a black shirt on a sunny day. Dark asphalt absorbs shortwave solar radiation and converts it into heat, so making the ground highly reflective should bounce that energy harmlessly back into space. Meanwhile, urban trees are supposed to act as natural air conditioners through a biological process called evapotranspiration, releasing water vapor that dramatically cools the surrounding air. For years, billions of dollars have been poured into these exact mitigation strategies under the assumption that they are foolproof, constant solutions to peak heat waves. I believed this too, because the surface temperature data seemed to prove that these interventions were an absolute triumph of modern urban engineering. This is science, where we chase facts, not legends. But when we look closer at what happens to the human body in these engineered environments, a terrifying problem emerges. When researchers actually measured the human experience of these cooling strategies, the results completely contradicted the established urban planning doctrine. Let us start with the highly reflective, cool pavements that cities from Los Angeles to Tokyo have been installing at massive expense. If you point an infrared thermometer at the white ground, it is undeniably cooler than the black asphalt right next to it. But humans do not live inside the pavement. We walk on top of it, and that reflected solar radiation has to go somewhere. Because the white paint is so efficient at reflecting shortwave radiation, it acts like a giant mirror, bouncing the sun's energy directly onto the pedestrians. Studies have revealed that highly reflective, cool pavements can actually increase the heat you feel on your skin by up to 7 degrees Fahrenheit. Instead of cooling the city, we have accidentally built a solar oven that worsens heat stress exactly when people are most vulnerable. And the situation with our million tree initiatives is equally problematic when you examine how biology reacts to extreme urban stress. The entire concept of trees acting as natural air conditioners relies on them having a constant supply of water to power their evapotranspiration process. But during extreme heat waves, which are almost always accompanied by severe drought conditions, trees go into survival mode to prevent catastrophic water loss. They close their stomata, which completely halts their evapotranspirative cooling effect exactly when the heat wave is at its absolute peak. So if white roads are cooking pedestrians and trees shut down when we need them most, what is actually driving the urban heat crisis? To find out, we have to look past the surface treatments and examine the fundamental physical geometry of the city itself. Let us start with what we actually know about the baseline phenomenon, which scientists call the urban heat island effect. Extensive global measurements confirm that urban areas are generally 1 to 7 degrees Fahrenheit warmer during the day than surrounding rural areas. But the real danger, the mechanism that actually kills vulnerable populations during heat waves, happens after the sun goes down. At night, cities remain 2 to 5 degrees Fahrenheit warmer than the countryside, completely preventing the human body from recovering from daytime heat stress. For decades, we blamed this entirely on the replacement of natural vegetation with impervious materials like asphalt and concrete, which have high thermal mass. But in 1982, a pioneering climatologist named T.R. Oak published a foundational paper that changed our understanding of urban microclimates forever. Oak defined a concept called the urban canyon, proving that the exact three-dimensional geometry of our streets is what truly traps the heat. He introduced a measurement called the sky view factor, which calculates how much of the open sky is actually visible from the ground level. During the day, the streets and buildings absorb massive amounts of shortwave solar radiation, heating up like giant thermal batteries. At night, these materials try to cool down by emitting long-wave thermal radiation back into the freezing vacuum of space. But in a deep urban canyon with a low sky view factor, that outgoing thermal radiation hits the walls of the surrounding skyscrapers and bounces right back down. The heat is physically trapped in a geometric pinball machine, completely unable to escape the city limits. But the trapped radiation from the sun is only half of the story. In 1999, researchers CSB Grimond and TR Oak demonstrated that dense urban cores have a secondary, entirely human-made heating mechanism. It is called anthropogenic heat flux, and it is the raw thermal energy generated by our vehicles, our industry, and ironically, our air conditioning systems. When you run an air conditioner to cool the inside of your apartment, it works by extracting that heat and violently blasting it out into the street. Grimond and Oak calculated that this anthropogenic heat contributes 1.5 to 2.0 watts per square meter to the urban energy balance. We are actively pumping localized exhaust heat into a geometric box that is specifically designed by its architecture to prevent heat from escaping. And the consequences of this trapped energy are becoming absolutely catastrophic on a global scale. In 2021, the Intergovernmental Panel on Climate Change, in their AR6 report, projected a terrifying future for the urban heat island effect. They highlighted that the loss of evapotranspiration combined with dense geometry will cause the heat island effect to intensify dramatically. Under the Shared Socio-Economic Pathway 2-4.5, urban heat is projected to intensify by approximately 0.4 to 1.0 degrees Celsius every single decade. By 2050, our major cities could be up to 4 degrees hotter than the surrounding countryside, pushing human physiology past its absolute breaking point. But here is where the science of urban climate becomes incredibly complicated and why simple fixes fail so spectacularly. If the deep urban canyon traps heat at night, the obvious solution would be to bulldoze the skyscrapers, widen the streets, and open up the sky view factor. But if you flatten the city and remove the deep canyons, you expose every single pedestrian to direct, punishing solar radiation during the peak hours of the day. We desperately need the deep canyons to provide shade during the day, but we desperately need wide open skies to release the trapped thermal radiation at night. Every single urban planner is trapped in this impossible geometric paradox. All of this evidence pointed to one inevitable, paradigm-shifting conclusion. The truth, as it turns out, is that you cannot paint or plant your way out of a thermodynamic trap. The geometry of the city isn't just the container for the climate. The geometry is the climate. In 2021, leading urban climatologist M. Santamoris published a comprehensive review of passive cooling strategies that finally cracked the code. What the evidence shows is that the optimal urban environment requires a highly specific, mathematically precise asymmetry. You cannot just apply a single solution universally. You have to navigate the geometry trade-off block by block, street by street. To survive, a city must combine deep, asymmetrical canyons that cast continuous daytime shade with highly specific ventilation corridors that allow nighttime heat to blow away. When cities implement these complex, geometry-first passive cooling strategies, the results are staggering. Santamoris noted that this structural approach can reduce peak surface temperatures by 2 to 5 degrees Celsius permanently. It wasn't about finding the perfect reflective paint or the most drought-resistant tree. It was about understanding that every single building we construct acts as a permanent, immovable climate machine. This completely changes how we must approach the future of human habitation on a warming planet. For decades, we treated the urban heat island effect as a superficial problem that could be solved with superficial bandages. We assumed that if we just mimicked nature by painting things white like snow or planting trees like a forest, the physics would simply work themselves out. But an urban canyon is not a forest, and a paved road is not a snowfield. If we don't navigate this geometry trade-off immediately, the urban heat island effect will continue to intensify by nearly 2 degrees Fahrenheit per decade. We are literally building the ovens that will cook the next generation of city dwellers. This urban heat crisis reminds us that nature does not care about our intuitive, easy fixes. It only obeys the ruthless laws of thermodynamics. But the urban canyon isn't the only human-made system that is secretly working against us. I'm here to help you know the systems shaping our universe. What urban design failure drives you crazy in your city? Tell me in the comments. See you at the next foundation.